Hello students, we were discussing the synchronization mechanism, basically the code acquisition mechanism inside the frequency hopping spread spectrum communication receiver. And in the last module we have seen the detection probability expression, false alarm probability expression, and the expression for the missed detection. And we have also discussed the first method of FHSS code acquisition system, where we have deployed a match filter based architecture. We have analyzed it and we have seen that match filter based code acquisition scheme in the FHSS receiver can give us very nice and very fast acquisition. So, time of acquisition is very less, but the main problem was that the whole architecture is very much hardware intense, and the false alarm probability or the rate of the false alarm may be very high in that system, in the match filter based system. The whole architecture gains in terms of the acquisition time because the processing goes on parallelly. So, with respect to the serial search mechanism, the gain is there over the over h times, whatever be the number of the hopping tones are. So, in the order of that, approximately you will gain in terms of the reduction of the acquisition time with respect to the serial search techniques. We will today discuss the second mechanism of FHSS synchronization. We will quickly revisit the incoming signal model that we took in the last module. Please remember, we were discussing based on the push to talk network and push to talk communication setup, where we understand that the communication is going on in the burst mode, where the voice messages will be transmitted at a particular time. Then there won't be any communication over the network over an extended period. Again, once the data is enough in one end, on the transmitter end, second burst transmission will be going on. So, that is the mode of operation, and we also understood that because of this silence period involved in between two communication within the network, there is a high possibility that the synchronization that was established during the previous communication between the transmitter and the receiver, that will be completely lost when the next communication will be happening, next burst communication will be happening. So, in a communication network, burst type of communication network like PTT or push to talk network, it is essential that for each and every transmission you align the signals in the transmitter, you align the code in the transmitter and the receiver. So, synchronization becomes much more critical in a burst communication or a push to talk and push to talk kind of communication network. And in view of that only, we are going to discuss the second method here, because we understood that in the first method, though acquisition time got reduced, but false alarm rate has increased and the hardware complexity has increased. We took the model like this, that suppose we have capital H number of the hopping tones involved in the synchronization sequence, and hence the received signal over the kth hopping interval of the synchronization process. We wrote the equation like this. We also discussed that in this equation, Rk is the received signal as well as the transmitted signal on the kth hop interval. Capital R, this is the average power inside the signal. Fk is the frequency of transmission. Theta k was the carrier phase associated with it, which is random and usually uniformly distributed. Nk is the additive wide Gaussian noise process with the variance sigma square, and we know that as we have considered the mean of this process to be equal to 0, then sigma square is equal to the power of the noise. Okay. We also found that by the definition, the detection probability will be given by the expression 1.2, where the test statistics that it is the detection probability is the probability that the test statistics Z crosses the predefined threshold value gamma th inside the correlator detector architecture. And this probability function can be approximated, well approximated by the Q function, which is where Q function is Q function parameter is having a dependency on two basic parameters. One is the nu, another is the gamma dash, where nu is nothing but the sum of all the SNRs of each and every hopping interval or every hopping tone. So, we use the sum of over all the hopping tones, and Rk is basically the power received over the kth interval. So, in that sense you may actually you may like to actually change the incoming signal model in the first slide to be not exactly equal to R. You may actually, for your easy understanding, you may actually write it as Rk, because that is the power received with the kth interval associated to it. And that Rk is now getting, for each and every path you are taking that Rk and normalizing it and dividing it with the signal noise power, and it is equal to gamma square sigma square, as we have discussed that we have taken the wide Gaussian noise process mean value to be 0. And similarly, the gamma dash to actually we discussed that gamma dash is the normalized value of the gamma th, the threshold selected, and the normalization is done with respect to the noise variance or the noise power, because we did this step to minimize the false alarm probability rate, and hence finally the detection probability becomes a function of this normalized threshold and the total SNR values, and it can be well approximated by the Q function. That was the understanding about the detection probability. And we also saw that the probability of miss hence will be given by 1 minus the detection probability, and this analysis included over a Russian fading channel, and where the interferers are present, the jammers are present, and all other receiver side imperfections, they are also present. So, in this environment of a PTT, where the PTT network operating over a Russian fading channels in presence of the interferers, jammers, and other different kind of the impurities, and all the impurities on the RF front end receivers are also playing a very big role in the detection process itself. In such an environment, during the hop interval number k, the received signal we saw that we can write down like this, where this first part is basically the contribution from the direct line of sight path between the transmitter to receiver. This guy says actually the power that it is a contribution from the multiple paths in the wireless environment, and this is the Gaussian noise process getting added. We also discussed that there is a bandwidth BIF, which is a noise bandwidth, and eta 0 by 2 is the two-sided power spectral density of the noise, and sigma square hence will be given by N0 into BIF. So, with this recap, we will enter into the second mechanism of the code acquisition in FHSS, which is called the serial search. This serial search employs the active correlators. We understand that match filter is a passive correlator based architecture, and now we will go ahead with an active serial search correlator based search mechanism. And such a correlator can be seen like this, can be observed in the next slide. Here is the active correlation architecture, and the integration time inside the integration time is after the low pass filter and the squaring up and all, the integration time inside the whole correlation activity, that integration will be designed and it will say already set by the hop intervals equal to Ts, which will be fundamentally the h times of the hop interval, and this is the total interval or the integration time or the observation window over which the decision will be taken, search will be continued. If the receiver now is in sync with the incoming signal, then all these h hops periods will contribute to the test statistic z, and when z rises above this threshold, then you will be declaring that there is a sync lock. So, thing is something like that, that continuously the incoming signal is getting correlated with the locally generated pseudo random sequence. After bandpass filter and this non-coherent detector architecture, the output of this guy, the in phase and the q phase components, they are integrated over a duration of 0 to 3h, over a duration of the hopping interval, and each of that hopping interval output is now getting compared with the predetermined threshold, and once actually it is crossing it, the control will declare that there is a sync lock happened. But remember the stuff that once you are actually you are basically depending upon the statistics of this z2. If this z2 is whether z2 will rise above the threshold of predefined threshold of gamma th1 or no, will be below that, it largely depends upon that whether the output of the hops, how the output of the hops are contributing to form the value of this z. Suppose it is such that none of these hops are significantly contributing to the test statistics z, then the total output of all of that won't be sufficient to cross the predefined threshold value gamma th. And it may happen that if some of the receiver hop frequencies they do not coincide with the incoming hop sequences, then during those periods there won't be any match. The output of this squaring envelope detector will give you perfect 0. Basically, actually output of the square envelope detector is coming, will give you some value if this guy incoming signal and this locally generated PN sequence for a typical hop perfectly coincides. So, suppose I have 1 to capital H number of hops. Okay. If I see that when the received signal is coming over hop number 1 means frequency hops and corresponding frequency hopping sequence is f1, frequency associated to it is f2, and frequency associated to capital H is f8. So, if I see that the locally generated random sequence is exactly in sync with f1 when the hop is going on over 1, then definitely at the output of the both I and Q detector I square law outputs of the both I and Q path will give a significantly high value, and it will contribute actually significant way over the contribution over the constitution of these values test statistics z. But think a situation that for most of these hopping patterns and hopping frequencies, the locally generated noise sequence, the generated code is not aligned with it. If they are totally out, then the square law detector output will be very low, close to 0. And if it is 0, then for those hopping frequencies, the contribution to of the z will be very low. And hence, if I add up all the values of the z from 1 to capital H, if for large number of the cases you are totally misaligned to the incoming signal, and most of the cases hence the detector output has produced perfect 0 for you, then this total value inside the z parameter won't be much, and it will be difficult for the z statistics these test parameter statistics to cross actually the gamma th value, and hence the synchronization won't be locked. The control needs to readjust the clock in such a way that most of the favorable situations, most of the hop sequences you try to get aligned with it, such that the output of the detector is improved. Think completely the opposite situation. If you have a perfect sync situation with all the hopping frequencies, then for all the cases the detector output will be really high, the value of the z will be also very good, so that the gamma th, it will be, when comparing the part, gamma th output will become very high, and hence controller will declare the sync is locked, so that it will keep the clock phase exactly the same that you kept in the earlier time span, and keep on generating the pseudo random sequences that is going on. Okay. So, question is actually if a sufficient number of the hops are not they do not match. So, we understood that z will not be above the threshold, and control will now readjust the clock. Actually, when there is no crossing above the threshold, the test parameter fails to cross the predefined threshold, then the controller basically holds back the clock for at least one period, and thus slipping the code sequence by one chip, and this process is repeated until the correct code phase is found. So, one by one chip slip actually is going on till actually most of the z parameter value of the test statistics, that z value improves and you get actually a sufficient high value to cross the threshold. Till that point, the control circuit keeps on holding back the clock and continuously one by one chip by chip basis the slipping goes on. So, it is just adjusting of the clock with that, and remember, as it is going on in a very serial fashion. So, it requires the control circuit may require long time to declare that there is a sync clock, because it never at one step it never declares or it never actually decreases the clock phase by several chips. Generally, by declaring that the synchronization on a single successful attempt is there, if I find even that actually that over a fast slot or fast loop or fast dwell time, within a first dwell time, that synchronization is locked. But serial search acquisition mechanism never rely on a single dwell based declaration of the synchronization lock. It is not actually advisable also to lock it there, if you even if you find that in the first slot, even at the last slot immediately actually after getting the first one, you have got the lock. We try to actually see it over the multiple dwells, over the combination of these H tones. We try to check it over the at least 2 or 3 times whether the lock is genuine lock or not. I mean all the cases whether your test parameter statistics z is crossing the gamma th value or not. So, it is a serial search technique not only actually needs lot of time within a single search time if the alignment is not matched, but also actually even after getting locked, it does not declare it to be locked, and it takes a lot of the other time. It takes actually several iterations to finally declare that there is a sync lock. So, typically here you will see that sequential successful synchronization indications are basically required, and remember it is a sequential indication and it is a serial search mechanism. And if we see that for the very steep serial synchronization, the probability of the false hit on a single attempt, already we have seen that this expression gives the probability of false alarm. We understood that probability that there is no sync, I mean the false misdetection is there given by this expression. We established this expression in the last module. But remember, when the false alarm you are declaring, you have to substitute capital H is equal to by capital A, and this gamma dashed will be basically the threshold level gamma th2 or gamma t some other threshold value that you are adjusting inside the comparator. And but remember, here we are talking about the m sequential successful synchronization indications. So, if I ask what is the total false alarm, that will be given by this individual probability of false alarm raised to the power of small m, obviously. Similarly, the overall probability of missing the detection, if it is given by the expression of no synchronization, it is right. So, it will be in obviously 1 minus the probability of h whole to the power small m. This probability of h, p of h is basically 1 minus probability of no sync when for the one dwell time based synchronization indication or decision take based on one sequence. 1 minus p and no sync is given, actually it gives that there is a probability of overall probability of missing. And see, actually if I am having, just a minute. So if I am having this expression given to us, where this p of no sync, I mean the misdetection, will be given by this expression, then overall misdetection I will be able to get by 1 minus p of h whole to the power small m. And remember here that receiver may be knowing what exactly the code is, but receiver doesn't know that where inside the sequence the incoming signal is located within that sequence. So suppose in practice, let me give an example that how much search is required in a practical PTT kind of the networks. Say usually they utilize a 256 frequency hops, and so search is required over 256 hop intervals, and to suffice to find where the sequence is in this pattern, and remember, if you try to deploy the whole search mechanism by a structure of match filter, you need 256 parallel match filter architecture, and very shortly you will get the acquisition time. Within a very short acquisition time you will get the result. But remember, actually the hardware complexity involved in the 256 parallel match filter architecture, whereas here 256 serial search will be required, and that also is over a small m number of the consecutive checking of the process, even if you get the synchronization lock to happen within the first dwell time. So serial search, actually in terms of the time consumed, serial search over 256 frequency points is really very high, because that's why actually we call the serial search process is basically very slow process, but it's a probability of finding the code sequence is really very high. So I mean that probability of the false lock will be very low, because you are serially searching all the frequencies, and that also you are repeating over the multiple dwell times, and so the false lock is very low. Whereas in the match filter based architecture, at one shot you are trying to see all the frequency points with a typical delay, and you are trying to declare whether the synchronization is achieved or not. So your false lock probability is very high, acquisition time is very less. In a noise free case, actually the serial search mechanism can give you the guaranteed correct code acquisition or correct code location. Basically that's why in the practical system deployment, we always be very critical about choosing the mechanisms, because sometimes the acquisition time becomes very critical based on the kind of application we are doing. Sometimes actually and that moment the hardware complexity doesn't play any role, but sometimes actually the perfection in the code acquisition becomes very critical for us, and we do not go ahead and do not care about the acquisition time that you are sparing to give me the correct acquisition. So in that situation you go ahead with the serial search. On the top of all that, the number of the frequencies or the hop frequencies you are going to search, that plays another important role. Even if actually my acquisition time is not a very big point or very big point of our consideration, but remember one thing: if the number of the hop tones increases even greater than 256, if it becomes 1024 and all, then in such a situation, even if you are giving me the relaxation of maybe not restriction, putting any restriction on the acquisition time, but then also I will be very much critical of choosing the serial search mechanism, because I understand that most of the time, and hence the bandwidth will be totally eaten up because of the synchronization process, because serial one will not only take the decision over one search over all these 1024 frequency tones, and it will actually repeat this 1024 point search over the multiple times. So, the acquisition time is actually linearly increasing over the tone of the frequencies, the hop frequencies, as well as the number of the times you are choosing actually to repeat your estimation process and the synchronization decision process. So, even if actually in the practice you are giving the relaxation over the time or the complexity, please try to take a crucial call by looking nicely inside the number of the hopping frequency involved in that synchronization process. And sometimes we do actually some mixing up of this architecture, reducing the architecture, and I mean that we try to get the good effect or the plus point of the advantages of both the mechanisms. We will decide it in the and discuss it in the next module. And now about getting about the average acquisition time for the serial search based active correlator architecture for FHSS. This acquisition time, here the expression, if you see that it is h into th, but here the NC becomes, the search becomes m times, and so here the linear increment is involved compared to the match filter based architecture in the acquisition time. And NC basically is the maximum delay difference that you are having between the received and the locally generated. It is in terms of the code chips actually we can count this delay. And let us take a good example also in the next figure. We will see that when two number of the sequential searches, means 2 times the search was repeated, and if we keep the probability of false alarm fixed to 10 to the power minus 4, the probability of the missed detection for the serial search technique, let us see in the next plot. See, this is something when you are varying the number of the hop frequencies from 30 to very high, that is very low, and you are keeping the probability of false alarm 10 to the power minus 5. These are the other parameters set for the experiment. And when the thresholds are changing from 14 dB to 19 dB slowly, you see that the synchronization missed detection probability, actually it is reducing. It basically reduce if you increase signal to noise ratio. But remember, if we are increasing, for all the cases we have kept the number of the search values same, but this averaging is going on. Actually, if I am increasing the number of the tones, so the value of the parameter z, the chances that the z you get the accumulate the value for the test parameter z over increases. The value of the z, a chance that the value of the z will cross the threshold value increases if you have a higher number of the tones also to go ahead with. So, that is all about the active correlator based architecture and its performance analysis approximately in the superficial way. And to understand what the basic architecture is about, how does it work, and where the problem is in between the serial search technique as well as the match filter architecture. And we realize that serial search technique basically improves the detection probability and reduces the false alarm at the cost of very high acquisition time. So, neither the match filter will be a single solution for all the practical problems, nor the serial search technique will be actually a unique solution for all the different kind of the application in the practical cases. So, in the next module we will learn something new. We will try to combine both the architecture and try to see whether we are getting some advantage out of that combined network or combined architecture or not.